to 12 Lab 3 circuitry by Jackson Greencorn. Let's get into it. We're going to keep this introduction brief, but basically we're using conservation of voltage, current, and energy through loop rules and node rules to understand the differences between the wire that we made in a lab setting versus an idealized wire in an idealized setting. We're going to be using a couple of assumptions such as equilibrium and steady state. We'll see how that affects our calculations. For our fundamental equations, using Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law, and the RC equation, each with their respective understandings and rules. Here are a couple more equations. We're not using inductors in this lab, but we are using resistors and capacitors, since capacitors and resistances in series versus parallel are very crucial to this lab. The results we found was that the delta V across the complete circuit summed to 0, which is great. That coincides perfectly with Kirchhoff's voltage law, saying that all the sum of voltages in a complete loop should equal 0, since if you take the delta V of your start and your finish, where your start equals your finish point, it's going to be 0. Something similar to average displacement over time. Measured current equaled 0.0065 amps. The RC equaled 9.12 seconds. And if we increase the RC, it increased both the charging and discharging time, since if you hold delta V and delta V naught constant, that means increasing RC means you have to increase the time variable on the other side of the equation. For the DC experiment, we constructed a DC circuit using two resistors, 47 ohms and 100 ohms. Our prediction was that 2.9 ohms or 2.9 volts due to Kirchhoff's voltage law and 6.5 milliamps or 0.0065 amps. Since in series, the current 1 equaled current 2. The measured current, 6.5 milliamps and negative 6.5 milliamps when reversed, but that's only a directionality convention. For the measured potential differences across the 47 ohm resistor, 0.31 volts, 100 ohm resistor, 2.21 volts, across the wires, 0, and across the ammeter, interestingly enough, 0.49 volts, and then when you sum that, you get 2.89, and then that's obviously the V total, so 2.89 minus 2.89, 0, coincides perfectly with Kirchhoff's law. Here's a graph explaining that very thing. And then here's the picture of what we did in lab, and then the measured resistances of each using Ohm's law, R equals delta V over I, using I equals 0.0065 amps. 47 ohm, you had 39.13. The 100 ohm resistor, you had 324.64. The wires were 0, and then the ammeter was 75, and we'll get into this in a little bit. Secondly, we constructed an RC circuit using a 10 ohm bulb, 20 ohm bulb, one 9-volt battery, and a 200 microfarad capacitor. Our observation was that the bulb was bright initially and then dimmed over time as the capacitor charged, which makes complete sense since at time equals 0, the current's flowing into the bulb and the capacitor is not charged, but as time goes on, the capacitor is actually taking more of that charge away from the bulb, and therefore the bulb light dims. Measured times 14.83 seconds and 11.2 seconds for the charging and discharging of the 10 ohm bulb, respectively. And then for the 20 ohm bulb, 57.25 seconds for charging and then 46.3 seconds for discharging. For our RC equation, going down the line, solving for RC on this side, and then we noticed that our delta V dropped to 24% of its original value. So RC of charging, negative 14.3 over natural log of 0.24 yielded 10.39 seconds, and then RC of discharging equal to negative 11.2 divided by the natural log of 0.24 equals 7.85 seconds. Taking the average of that, we found that our average RC was 9.12 seconds. The assumptions that we made for this lab was that it was in steady state, which meant the electron current was constant, so that the derivative was equal to 0, and that it was in equilibrium, so that charge distribution is equal with no external forces pushing the electrons through the wire, because if this were to happen, we could not use Ohm's law and node rules, but we wanted to make sure that we could do these so that they apply. Possible errors since the battery health. The batteries were not new. Our voltages were slightly lower than some of our peers. Their voltages were significantly higher than ours. But another thing was human error. Timing of some of the charges were off and therefore inconsistent with the calculations that were made using them. This has been Lab 3 Circuitry. Thank you very much.